The first thing I want to mention here is that you have access to quantum computers right now online. We have them available in the cloud, and you can start programming them for free. Particularly if you're willing to open source your software project programming the quantum computer, you can actually continue to get access. You can upgrade your account to a developer account and continue to get access every month. We've also actually just created a new initiative for those of you who are working on projects associated with COVID-19 responses. If you're helping companies or hospitals with their logistics, we've actually created a special login screen, and you can get as much free access as you want to the DWave quantum computers to help you with those programs. So check that out as well if that's the kind of work that you're doing right now. And the other thing is that, having been to some GOTO conferences and talked to a lot of the attendees, what's really interesting is like what's at the cutting edge and what is kind of just in the future. What should we be preparing for? So this is the year when DWave is going to launch its next generation quantum computer. It's going to be it's going to have 2.5 times as many qubits as the largest quantum computer you can purchase right now. It's going to have about 7 times as many couplers, and it's going to be the largest, most powerful programmable quantum computer that's available in the world today. So this is a great time to get started and exploring the resources that you have, because when that starts coming out, you can bet that there's going to be a lot of questions in the community about how do we apply this to business and to the problems we want to work on. So in that note, I'm going to try to connect this to some simple examples, give you a bit of a sense of like the overall examples and applications this is applicable to, and then we'll take a dive into the technology and show you just how much of that is accessible to you yourselves. The key here is that, over the last 20 years, there's been a lot of research and development focused around building out the technologies and getting them to the point where you could actually use it as a recognizable computer. And 2 years ago, some scientists at NASA and the University of Texas were able to show a 100 times speed up on some benchmark problems relative to a whole suite of classical heuristic alternatives. Those were the best available classical codes for competing with quantum computers at that time. And move forward 1 year, about a year ago, we published work in the journals of Science and Nature on quantum material simulation. And last year, we were able to show that those computations are 3 million times faster than the best classical alternatives. And that's exactly the milestone that people are looking for in terms of, okay, if those kinds of computational speedups are possible, how do we harness those in our applications, in our businesses, in our missions? So that we can leverage that and get high quality performance with new products. So that's the point that we're at right now. And with the Advantage system coming out, that's the next generation quantum processor system coming out this year, we're working with customers and partners to help them see Advantage in application and helping them to build end-to-end applications. So that's the sort of point in time we are right now. Online, we've got our Leap cloud services. It's a combination of access to the quantum computers themselves and hybrid systems, which combine classical and quantum systems together, as well as a quantum application environment, which is trying to pull together the SDK, the tools, and the integration to make it really easy to learn and get up to speed building quantum applications. In February this year, we launched Leap 2, which was a significant evolution on our cloud services online. And with that, we added in a product which allows users to solve problems that are effectively 100 times larger than anything they've done before. And it does this by deploying cloud resources, both quantum and classical, and combining those two technologies in the best way possible to get users high quality answers. In addition to that, we've actually incorporated an integrated developer environment in Leap so that it's the simplest it's ever been in terms of getting started right away with the SDKs. And we've actually published several open source examples to help people get started on their applications. And finally, with this Leap 2, we've also incorporated a problem inspector. So this allows us to actually see the problems that we're sending and the answers back that we're getting from the quantum computer. So we can see the relationship between what's actually in our problem itself and what's getting passed down to the quantum processor, and then interpret the results in the context of that relationship of how we're trying to program it. And by the end of this presentation, I'm going to show you a little bit of that myself. There was a researcher, a really talented researcher named Ewan Tang at the University of Washington, who basically made a really important observation in a blog post that she was making, which was that the most sought after quantum algorithms are the ones that provide quantum processing while still accepting classical input and providing classical output. That's what made Shor's algorithm such a breakthrough in quantum computing, because you basically provided a number like 15, it tells you back the factors of that number are 3 and 5. Everybody on the planet can interpret those answers, but it's actually using quantum effects to accelerate the calculation from the input to the output step. And that's the whole model for DWave quantum computers, is that we don't have to, as programmers, learn complex amplitudes or complicated matrix transformations. We can actually put in, use Python programming to send data that we can interpret into the system and get answers back out again. So what's the name of the game? What makes quantum computing different from classical computing? And what are its capabilities? What is it really good at? Because it's important to know that every technology has its strengths and its weaknesses, right? We're not trying to do what classical computers can do really well with a quantum computer, because classical computers have a huge advantage. They started their development 60, 70 years ago. So the key thing here is that when you're working on a problem where the answers to what you're looking for define a huge solution space, a quantum computer can search that solution space for you very quickly and return answers. So imagine that we actually, as a programmer, set in a landscape basically saying the high energy solutions, those are penalized. We don't really want those. They're not high quality. And the low answers, the ones at the bottom of the landscape in the valleys, those are the high quality answers we're looking for. The quantum computer will search all of those and then return to us points in the valley or in multiple valleys, letting us know where the good quality solutions are. Classical computers can also attempt problems like that, but what happens is that because the solution spaces grow so quickly, even the ability to sample 5 billion points in the landscape every second gets quickly overwhelmed with the fact that that's a small neighborhood relative to the space of solutions we're looking at. So, even small quantum computers with 300 qubits can explore solution spaces that are larger than the estimated number of particles in the universe. So that's what I mean by a large solution space. Okay, so let's look at how that gets done. I'm going to build up a really simple example. It's one that I've talked about before, but I've included a couple of other steps. It's a network of pipelines. So imagine we're working in an industry where we have a pipeline network and we want to purchase sensors so that we can monitor each of the pipeline segments to make sure that they're operating correctly. And we're going to place those sensors at the junctions. So we want to make sure that we select junction locations like 2, 3, 4, and 6 here, which allow us to cover every pipeline segment. And we want to do that at the minimum cost. So we don't want to buy more sensors than we absolutely need to. So let's break this down into 2 relatively simple steps. The first is we're going to track each location where we place one of these monitors. And we're going to use a binary variable to let us know whether we've placed a sensor there or not. So at junction 1, this binary variable x1 is going to be 0 if there's no monitor, and x1 is going to be equal to 1 if there is a monitor. So that's nice and easy. It's a simple binary variable. If we want to figure out the cost of all the monitors we've purchased, we just add up all the binary variables for all of the junctions, x1 through x7, and that tells us how many monitors we put in the system. So if we want to write that a little bit more compactly, rather than listing all the plus, 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 plus out, we can just use this summation. So this big sigma just means add up across all of the x's where every I is one of these junctions. Okay, so that's actually placing the monitors. Now we have to make sure that we're actually monitoring the network. So for every pipeline segment, we have another decision to make, which is that we want to make sure that there's a monitor at either one end or the other, or both. But we don't want to end up in a scenario where there's no monitor on either end. We haven't covered that pipeline segment if that's the case. So this simple formula I've written down here, I mean, I didn't come up with this myself. We actually have software programs that will tell us what these formulas are. This one basically captures that. So I can show you that for all of the 4 possible conditions of, no monitors, monitor on end 1, monitor on end 2, or two monitors, I can actually evaluate this equation, which I've done here, and show that the highest energy solution is the one where there's no monitor. So that's the penalty. Even though it's penalty 0, that's a penalty because any other configuration has an incentive. It has a negative penalty, which is basically trying to move in that direction. So this equation is basically trying to set up the scenario where either one end or the other or both are monitored. And then we can just take that thing we've worked out with that formula and then just apply it to every pipeline segment here using the variables u and v to represent either end of the junctions. And then again, like we did last time, rather than adding them all up with a long equation, we're just going to put a summation in here. So that's basically everything we've done to set up this problem. It might seem deceptively simple, but the fact that these variables are binary and that the choices of where the monitors go in depend on other ends, they're coupled together in these pairwise relationships, that puts this problem into a class that's exponentially difficult to solve. So, so let's combine these together in a mathematical form here. We're going to take adding up all the monitors replacing, plus making sure that we've actually got the sites monitored. We're going to say, okay, we want to minimize the combination of these two formulas. And I've just put in basically a real number here so we can change the relationship of whether we want to reduce the cost or whether we want to make sure that everything gets covered. And then instead of writing that out as a long equation, I'm just going to take all of the coefficients, the numbers multiplying each of the variables, and I'm just going to put them into a matrix. So for instance, a -1 is going to be like a coefficient of -1, and then a 1 in front of these two is just going to be a 1. If I add up all those coefficients, I'm actually going to get a matrix like this, which should be familiar to, I think, most programmers. That bottom part here, these coefficients, that's all it takes to send a quantum machine instruction to a quantum computer. Okay, so that is if you were hand building this, but we want to get to applications much faster than that. So we've actually written an open source SDK, which allows us to do this in a much more compact program. So here we're actually leveraging existing open source packages. NetworkX is a package that was developed by Los Alamos National Laboratories. We've created some extensions to it, the DWave NetworkX package here, which includes connections to the quantum computer, as well as these codes here in DWave system to get that connection. So we've taken the DWave quantum computer here, we've put it through a translation layer, and then we've defined our problem. This is our application data, which we've actually just written out here, but could be ingested from another program. And then we've said, okay, this DWave extension to NetworkX, we want you to do the min vertex cover on that problem graph, given the connection with the quantum computer. So it's much easier to put these together using the tools than it is, let's say, building all the instructions up by hand. But depending on what level you're interested in, you can sort of come in at any point. So that kind of gives us a bit of a window into the structure of our open source SDK, where we have classical and quantum compute resources. We want to put those together through access points, let's say for the quantum ones or for the classical programs or combinations of the two, to form a problem form that's suitable for quantum technologies, but is not technology specific. And then when we're looking at it from an application standpoint, whether we're doing social network analysis or scheduling, we want to then pass that down through these mapping methods, either graph mapping, which was the NetworkX package I just showed you, or our constraint compilation, to get that into a form that's suitable for these technologies. So if you're interested, I mean, I've been to quite a few conferences, and the feedback I've gotten is, let's just look at more examples. So we've actually open sourced a set of examples on GitHub. We're working on improving and expanding that set continuously. Go on, check them out, send us issues and pull requests, create your own. There's a template there for creating your own, and see how you can kind of get started in terms of the different things you can use programming the system. So with that, let me now expand out. That was a very specific, simple example looking at pipelines. What I want to sort of highlight here is that is just one example of many of physical network optimization. So these are systems where you have nodes in a communication network, or antennas that you want to place, or satellites that you want to sort of configure in a way where they interact with one another in a network, where you're either selecting something or you're not selecting something. Some component in your communication network is failing or it's not failing. Those are the binary elements of those physical networks you're looking at. And because they're connected in a network, they're interdependent. That creates this vast solution space that the quantum computer is going to help you search through. And then zooming out from that a little bit further, physical networks are just an example of network optimization more broadly. So I have physical networks up on the top right here. Other systems like material structures, when you have things that are bonded or not bonded, when you have neural networks where the neurons are either firing or not firing, if you've got social networks where individuals are connected together in friendly or hostile relationships, those are all examples of networks where there are important optimization tasks to be done that are quite complex for classical computers to do. And that has been borne out over the last 10 years. We've been working with customers. They've developed 200 early applications, many of which they've published information on in these areas of material simulation and material properties, machine learning, optimization, cybersecurity, and fault detection. So there's not enough time to go through them all. I'm just going to try to show you the places where you can go to see more of these resources. And also, you know, quantum computing has spent a lot of time in the R&D phase. We've actually gotten to the point now where we've actually run production applications. So this is an example of where the Web Summit conference buses were getting routed and rerouted. Their routes were getting optimized in Lisbon in real time using our quantum computer. And the CIO from Volkswagen had set that up so that it was actually interacting with several other technologies, iPads that they had in the buses, and then querying our systems in Vancouver to get live updates on how their routes should change. So we're definitely in the realm here where end-to-end production applications incorporating quantum computers are possible. Okay, so with that, I'm going to exit out of the presentation slides. And we're going to move to the live component here in the tour. So I'm actually in the DWave facilities right now. And behind me here, you can actually see one of the DWave quantum computers. So that system back there is a little bit taller than me if I was standing up. It's about, for those of you in the US, it's about 10 feet tall. For those of you from Europe, it's about 3 meters tall. It's a reasonably large system, and in front of it, there's actually some data racks, which I'm actually sort of gesturing to right here. For comparison, if you had a classical computer, if you were interacting with a high-performance compute cluster, and you had just one of these data racks in the front, fully populated with CPUs and GPUs, it would consume about 100 kilowatts of power. So relative to like one of those racks, this entire system is quite low power. It only consumes 25 kilowatts. And it's really interesting. We've actually gotten a lot of funding from the Canadian government because we're based in Canada, although we have sites in the US as well. Because this is a green technology, computing and compute infrastructure actually consumes a lot of power consumption around the world. And this actually consumes a lot less power to do its compute. I'll explain a little bit of that when I show you some of the internal components. Now, it's a little bit impractical to take you into the lab because A, it's very noisy, and B, those aren't actually open unless we're like swapping a chip in and out of one of the systems. So what I'm going to do is I'm going to share my screen and pull up a video that I've got all queued up. So this is a video that we created at DWave a few years ago that sort of provides a lab tour, and this segment here is going to actually sort of dissolve away the walls and show you some of the components and talk through what's inside here.
The room behind us houses the quantum processor, and the data racks in the front hold the quantum server where users can access and program the quantum processor. And the other data racks include the cooling system, which includes pumps and is responsible for the chirping sound you can hear in the background. Inside the room, before we get to the quantum processor, there are many layers of shielding which allow us to create the low noise magnetic environment the chip sits in.
Okay, now we switch videos. This is a segment just a little bit later in the same video here. So Jeremy, my colleague here, is actually standing right in front of the application server. So as I demonstrate to you how you can get access to these online right now in Leap, and we start programming the system, we're actually going to be communicating with one of these data racks. There's basically just a small set of them in here, and that's handling all the internet communication and taking control over the quantum computer when we're programming them. So this is going to show, you know, when we send a problem into the system, when you send problems into the system, where do your user instructions go, and how are things getting converted on their way to the quantum processor chip?
Users converting that into the machine language of the processor and sending that machine language into the room behind, where high precision analog electronics will convert those signals into electrical pulses, which are sent through cables into the refrigerator and down through the cooling system to the ultra low temperature of the processor. It executes this problem, and then data from the processor is returned to the server and returned to the user. And the system is very flexible, and that users can be programming in whatever language they're comfortable with, and interacting with it either with this system in their data center or even here in DWave's lab.
And this next clip here is actually a video of me a few years ago. So this is a system we had open at the time because we were changing the chips over. So I actually went into the system here. We had pulled away all of the shielding. I actually sort of explained what the different components are. So let me play this for you. This is a short clip. It's about 3 minutes long.
We're standing inside a quantum computer. And you may know that the quantum world is delicate. It's easily disturbed. So there are many layers of shielding in this system, which we've removed in order to look at the internals here. A traditional supercomputer may have many thousands of processors in it, but in this quantum computer, there's only one chip located right down here. When you send an instruction to the quantum computer, a delicate quantum calculation is taking place on that chip to produce your solutions. The system we're looking at here is an ultra-low temperature cryogenic fridge. Because it works at such low temperature, we use the Kelvin scale to measure how cold it's getting. In the Kelvin scale, a warm room is like 300 Kelvin, and 0 Kelvin is the lowest temperature that can be reached. Physicists refer to it as absolute zero. There's two levels of cooling in this system. The top one is a pulse tube refrigerator, which takes us from 300 Kelvin to 50 Kelvin, and then down to 3 Kelvin. This is roughly the temperature of interstellar space. And then a second refrigerator, a dilution refrigerator, takes us in this plate from 0.7 Kelvin, 0.1 Kelvin, and then down to 0.01 Kelvin. When the system is operating, this plate and everything mounted below it is 10,000ths of a degree above absolute zero, which is more than 100 times colder than interstellar space mounted here. And this whole system is designed to sustain those low temperatures in a continuous cycle. When you send an instruction to a quantum computer, the signals pass down these wires along the sides of the refrigerator. And at this point, there's a break in the wires where all the signals become superconducting. Superconductivity is this amazing effect where you can send electrical signals without any resistance whatsoever. So the electrons aren't even interacting with the atoms in the wires around them. That's great because it means that this portion of the system has no energy dissipation. It produces no heat. But it also means that we can't rely on the wires to cool the electrical signals and eliminate their noise. So we have a custom filter bank mounted here which cools those electrons. An important aspect of the superconductivity is that these signals and the quantum processor unit consume virtually no power, whereas the supporting systems around it consume about 15.5 kilowatts. And this remains the same regardless of which processors are installed in the bottom. If you were to take a fully populated server rack out of a traditional supercomputer, it might consume 10 times that much power. So for our first customer, Lockheed Martin, when they upgraded from their first chip to the DWave 2, they saw a relative performance improvement on the order of 10,000 times, but the power consumption for the system was the same.
I realize now I did mention 25 kilowatts, and in the video it says 15.5 kilowatts. That's the difference between when you actually started the machines, the peak power goes up to 25 kilowatts, so now the safer number to just refer to as 25, but when they are actually running in a continuous cycle, it's closer to 15.5. Okay, so with that, we're going to go from the super polished video element to the much grittier gorilla cam walking through our lab over here, and my colleague Tiani is going to help me out as we're moving through the system. And we're going to roll you over here. I'm going to show you some of the components that are actually from inside the refrigerators themselves. Here we go. So these are the components from inside the refrigerator, and this setup here is actually one of the wiring and filtering and chip packaging systems that you saw in the video. What's significant about this particular one is that this is the first commercially sold quantum computer. This is the DWave one that we sold to Lockheed Martin in 2010. And when this system is operational, everything you see here is actually at that base operating temperature of 10,000ths of a degree above absolute zero. I actually have one of the computer chips on its package just over here. I can actually pick that up for you. So the actual chip itself is mounted in the center square. And then we have some printed circuit boards around that, which are then taking the signals out to a set of connectors, which allow us to connect it to the wires and filtering. Let me show it to you like that. It's on a fairly heavy copper plate. And that plate is what basically takes the heat away from the chip in order to get it down to that ultra low temperature. The interesting thing about this technology, and that point I mentioned earlier, is that not only is the circuitry on the chip superconducting, but the wire bonds, the traces on the PCBs, the connectors, and then the wires stretching away from the connectors are all superconducting. So this whole system, when the chip is operating, is consuming 1/10 of a billionth of a watt. It's extremely low power. And this is why, as we upgrade our quantum computers from generation to generation, the actual power consumption of the computer itself doesn't change because the systems that we keep substituting in aren't actually consuming any power themselves. It's a sort of a fascinating feature. So let me pull this up here. Okay, so I can actually show you, I've got a microscope on this stand here, which allows us to see the image of the chip. My laptop camera is not quite good enough to actually see this level of detail when I'm just holding it up to the camera, but this is a 2,000 qubit quantum processor, the kinds that we have online available in Leap right now. And you can actually see this is the silicon chip, and then these are the superconducting wire bonds, which are then connecting the chip to the actual printed circuit board circuitry around it. And one of the nice features of this view, I'm going to pull you up just a touch closer, is that you can actually begin to make out that there's inside this active quantum processor circuitry area, you can actually make out that there's sort of like a square array structure. It's like repeating in a square array. And I'm going to show some of that to you over here. I'm going to show you one of the pictures we have of it. So here's another picture. And this picture here is showing you another microscope image of the quantum processor itself, and a little bit of a larger view. For those of you who have like actually taken classical computers apart at home, this is starting to look familiar because actually this is what CPUs and GPUs look like, because they're also fabricated, their circuitry is fabricated on silicon wafers. So I actually have one of the silicon wafers right here. And then a clamshell. Let me crack this puppy open. So this is an 8-inch silicon wafer here, and this actually has about 100 quantum computer chips. So at about $10 million a chip, this is about $1 billion wafer if everything was perfectly yielded. And each of these sites is one of those DWave 2000Q chips. I have actually talked to a lot of folks who do semiconductor manufacturing, and the trick is, the reason this doesn't cost $1 billion is because when we're doing fabrication, we're running it in a low yield mode. By which I mean that if we do, let's say, when we're doing a typical run, we might get 15 of those wafers every month. That's about, 1,500 chips. And then over about 3 of those runs, we might get like a half a dozen chips actually working. And then we'll actually run those and test them and get the design information we need to actually iterate on the design. So we're not going to run hundreds and hundreds of lots like you would in semiconductors in order to get like 99.9% yield, because our interest is in like really fast design iterations so we can learn from the design of a single system and then develop the next generation one. And we've actually gone through dozens and dozens of processor generations in the 20 years that we've been developing these systems. So this picture here is actually an image of a scanning electron microscope. So if I took one of the quantum processor chips and I like snapped it in half and then showed it to you end on, you'd actually see the layers, like the gray layers here are the metals, and then the dark layers in between, those are like the insulators. Those are like silicon dioxide or something like that. So that these actually form the different traces. And then instead of looking at it from edge on, if I looked at it from above, this is the imagery I would see in the layers of the actual circuitry defined on the chip. So that's how the quantum processors are manufactured. And the fact that we can make these superconducting quantum processors on silicon wafers is part of the reason why we can scale them up so quickly, because we can make use of like a multi-billion-dollar fabrication industry in order to leverage that and get this technology developed and built up much more quickly. Now, when the designers are going through and actually building out the quantum elements, they create these computer-aided design files. This is the CAD file that's used with the technology to print those wafers. So this is actually showing 4 different processor generations with some test structures in between. So when we get 1,500 chips a month, that's way too many for us to test at low temperature. So we test all the wafers at site here in order to figure out, okay, which of those 15 wafers is the best, and amongst the 100 sites, what are the best sites on the wafer? And then we dice out the chips, and then we put them into quantum processor systems. It typically takes about 36 hours to change over a chip with one of those systems. So you want to do as much of that testing at room temperature before you start doing the low temperature testing. Now, if I were to take this image here, and I mentioned before that there's sort of a square array structure to the quantum processors. If I took like one of the smaller squares and I zoom that out so that that formed this entire image, what we would see is this over here. This is one of those segments. So there's actually, in this graph of all the circuitry, there's actually 8 qubits. So a qubit is like the fundamental building block that is used to represent those binary variables. They're basically loops of superconducting metal, and if the current is flowing, I can't tell if I'm doing counterclockwise or clockwise here. This would be clockwise, I think. That's like a 0 state, and then if it's flowing counterclockwise, that would be like a 1 state. So that loop of superconducting metal is stretched out here, right here to form 1 qubit, and then there's 2, 3, 4 qubits down this way, and then the other ones are stretched vertically, 5, 6, 7, 8, stretched that way, and that's how we get 8 qubits together, and then this is printed multiple times across the processor to make the rest of the fabric. Now the reason I wanted to show that to you is now I'm going to go back over to my screen share. One of the features that sets DWave apart in terms of quantum computing systems is that there's actually a lot of information online about applications that you can use to program the system. I wanted to show this because the last time I was speaking with folks at a conference, they just said, I love the examples, but I'd love to see more and more examples. So we've actually created a site, a page on our website, which actually highlights application types by method or by industry. So you can actually search in here and find, telecommunications, and this will actually filter information from some of our customers and other people who've been programming the quantum computer based on that industry. And in fact, there's a nice one here from British Telecom, which is a presentation deck where they talk about how these really complex problems appear in telecommunications industry problems. I wanted to show you how to get access to the quantum computers right now. If you go to DWave Leap and click on any of these links, you'll find information about what's available in Leap and how you can use it to build and deploy applications. I won't go through that. We're actually going to go into it itself. Once you click on Take the Leap, for instance, it's going to take you to a sign-up page where you can go in and connect. And this is that point I was talking to you about. If you're working on a COVID-19 response project, you can enter there so that you can get as much access for free as you need to be able to complete that project. And we have about 13 other partners around the world, from Japan to Germany and all around North America, who are interested in working with people who are working on those projects and help them write their programs for quantum computers, because they have a lot of experience doing that. Once you do the sign up, you can get access to the system. I've actually logged in using my account here. So this is the dashboard, which shows you, some information you have available for when you're getting started. It shows you how much access you have to the system. So this is the amount of hybrid solvers that I've been using, but I can also look at my access direct to the QPU, how many problems I've submitted and how much time I have left to do that. Some details about my account and the system we have online here, it has 2,030 qubits, and it's at 13 thousandths of a degree above absolute zero. Now there are live demos that we can run in here, but I'm actually going to instead show you on the resources page. There's some information about the Ocean stack, including you can actually open up a workspace in the IDE with the SDK pre-installed. But also you can take a look at these Ocean code examples so that you can actually load them from there. So if I go to the Ocean code examples section, here we also have a searchable set, but these are only those that actually have open source code behind them. So if I search up the pipelines example, I'm actually going to see the example that we have. I can view the source on GitHub, or I can load this directly in the IDE. Now, I'm not going to click on this, although it's quite nice when we do that, because I've actually pre-opened it and I've actually injected a couple of components into that example. So here when I click start, or if I had clicked on that link earlier, it's actually going to deploy an environment with the Ocean SDK directly into it to allow us to run that example. And the reason I didn't do that direct from the source page was because I actually made a couple of small modifications to this program earlier when I was running the system. So this is a standard program. We've got our imports at the top, and then we've got our connections to the quantum processor here, where we're defining the QPU that we want to interact with. Here's our data from the example we were talking about that we're loading into the system, and here's that min vertex cover code line that I was talking to you about. So here's the trick, is that I injected this DIMOD import here so that I could use a tracking composite. And that's because this min vertex cover is like a higher level mapping function, but I actually want to be able to capture the problem that's going into and out of the quantum processor. So I injected that tracking composite to allow us to do that. So that's going to let me set a breakpoint here. And then I'm going to run this program in debug mode. So this is actually going to run right through and actually submit a problem to the quantum processor for us, and then we're going to be able to see the answer as it kind of comes back out. Okay, so yeah, it ran into some sort of problem there. So I'm going to actually go to our resources and build this up myself from scratch. Just like we talked about before, I'm going to go to the pipelines example, load this fresh in the IDE. I ran into some sort of problem with the debugger there that I don't want to try to fix live. So I'm just going to try to create a brand new instance of it. So we're going to see how fast I can type here in the remaining minutes we have going. So here's the pipelines version, deploying extensions. Okay, whew. We completed our test run. So there I just ran the code here. I wanted to make sure that this actually would run and submit to the processor. So that's what this did. And it answered back the min vertex cover for the network we were looking for are these junctions. So now I'm going to remove my terminal window and instead put a debug break here. And then I'm going to run this again in debug mode so that I can show you some of the instructions that are going into and out of the system here. Yeah, nice. Okay, so if I want to look at the problem that we submitted to the system, we're going to look at input, and that's the Q matrix. That is that sort of set of coefficients that I was showing you earlier. Those are the numbers that quantum processor needs to know what kind of network you're looking at and the fact that you want to do a min vertex cover over that network. And we can also do a print of the output here, and this is going to show us sort of like a quick print of all the different bit binary values returned from the processor, the quality of the solution, and the number of times that it occurred. But we created this inspector in order to make it a little bit easier to see what's going on here. So if I do dwave.inspector show sampler.output in the final minutes here, I'm going a little bit quickly, and I don't have a lot of time to sort of show you all the features of this problem inspector, except to show you that this is actually showing us the problem graph we're working on. This was actually the logical problem we were working on. We can actually search, if it was a big problem, we can actually search for variable 0, for instance, variable 1, variable 3, for instance, and it'll actually show us where that variable is in the graph we're looking at. And it also shows us the answers we got back from the quantum processor in a histogram. So the quality, the lower the energy is, the further to the left you are. And if you get multiple occurrences at one energy, they get stacked on top of one another. So we can actually see, as we highlight these different samples, how the variable values are changing on the left there. Now, in addition to that, I can actually click View 2 here. And this is where things get really interesting. Now, in this graph on the right, we're actually looking at the qubits and the couplers that were involved in solving that problem. And I wanted to show this to you show you that if I zoom out, you're actually going to see that everything that's available to you here is that DWave 2000Q processor graph I was showing you when I showed you the actual sample and when I showed you the picture of the processor graph. This is actually showing you the connection between the problem that we submitted and the actual qubits that were used and how they were coupled and connected together. So that's just a small taste of the examples and these extensions to really try to make these visual and interactive. And you can actually see how these like physical problems and optimization, like network optimizations that you need to be running, how they get translated into instructions on the quantum processor and solved for you. Sorry, I got into a bit of a hiccup there and I went a little bit quickly, but hopefully that helps.